So, hi everyone. It's great to be here at this workshop, not only because I work in mathematical foundations of equity, but because in a former life I was a transportation analyst. So I look forward to hearing some of your applications of fairness issues in transportation and maybe bring back some memories. Okay, so this is what this talk is about. How can we understand equity from a mathematical perspective? These are some of the people who I've worked with. There's a lot of recent results in this, and they are participants in that. So I'm going to focus on the issue, which I think is the main issue in practice, as to how to balance fairness and efficiency. We all like fairness, right? We all want to be efficient, too. We want to provide as much services as we can, but those two often come into conflict. And how do we balance those two? So that's the sticky issue, and that's the issue I'd like to try to address from a mathematical perspective. I'm looking for models of fairness modeling, that somehow in a principled way tell us how to balance these two objectives. Few applications. Obvious example is where do you put your ambulance stations or your fire stations? If you want to minimize average response time, you put them in the densely populated city core. If you want to minimize the worst case, you spread them out, but then that's going to really incur a cost on the average response time. How do we compromise between those two? Traffic signal timing, right? If we want to maximize throughput, if we have a major thoroughfare and a small side street, we'll give the major street the green light all the time. That maximizes throughput, but not very fair to the side street. Now, this problem is sometimes addressed with something called proportional fairness, also known as the Nash bargaining solution. I'll talk about that shortly. But it's one of the cases where engineering community has been on top of this fairness issue for some time. Telecom is one of the earlier adopters of fairness modeling. So here are some of the indices they use, including alpha fairness, of which proportional fairness is a special case. There we're trying to compromise between maximizing throughput and minimizing the worst case delay or latency in the signal. Disaster relief. There was a tragic example of this dilemma in Puerto Rico a few years ago. Hurricane Maria was the worst storm ever to hit that island in recorded history. And as a result, the power grid was destroyed. So there was the issue of how to restore power. Well, the policy that was followed, as I understand it, was to begin with San Juan and the big cities, restore their power first, because there you make the most efficient use of your crews, and you can restore power to as many people as possible, as quickly as possible. As a result, those in the hinterland, in the rural areas, sometimes went weeks or even months without power. Doesn't seem very fair, does it? But it was efficient, more efficient than it could be, perhaps less than it should have been. Well, yeah, do we need a more equitable solution, somehow balance these interests? That's the problem I'm grappling with. Okay. Now, in my field of operations research, we usually use optimization models to maximize efficiency or utility, minimize cost, and so forth. This can be very unfair. And just to give you a very simple example, suppose we have two individuals here and their utilities are shown here as contours. We're trying to maximize the sum of the utilities of the two, and we have some kind of budget constraint. Okay, so individual one has a cost of A1 for every unit of utility we provide, and similarly for individual two. So we get a feasible set like the green area there. Suppose we want to maximize utility, what do? We give everything to the more efficient guy. Okay, so A1 has what Amartya Sen called the conversion efficiency of 1 over A1. And most efficient guy gets everything. Okay, this is going on in all optimization models that use an efficiency objective. It may be obscured by the complex constraints, but the underlying objective is going to favor the very most efficient people and forget about everyone else. Okay. Now, how do we model a fair objective function? How do we do that? There's no one concept of fairness or equity. Okay, so we need to choose a model that's appropriate to the situation. So that's what I'm going to try to do here. I'm going to take you through a series of social welfare functions, or models of equity, that balance efficiency and fairness in a more or less principled way. And you can see what you think. Maybe this will be useful to you in your research. Perhaps you haven't seen some of these. You can see what you think. And I'm going to try to characterize these in various ways so we understand how they behave and help us choose which one to use. Okay. As we go along, I'll take a little excursion into social choice theory, which is one way of providing mathematical foundations for some of these. Okay? Now this, as I said, I'm going to focus on models that combine these two objectives. Well, why not just use an inequality measure and bound the degree of inequality? The problem is that that inequality measure gives us no clue as to how to balance it with efficiency. It just tells us, you know, be equal. How equal? We don't know. It just doesn't tell us anything about that. Why not use a convex combination of efficiency and fairness? Why not do that? Okay? Or efficiency and inequity. Well, the problem is you have to use a multiplier, you know, to take a convex combination, and you're usually combining two quantities in different units. For example, Gini coefficient is dimensionless, whereas utility is usually defined in terms of negative cost or benefits or something like that. Okay. So again, it's difficult to interpret what's going on when you use a convex combination. So we're looking for a social welfare function that combines these two. There's a long tradition in welfare economics of study of social welfare functions. This is a function that measures the desirability of a distribution of utilities to all the stakeholders. It takes into account the absolute amount of utility, how well people are doing overall, and it also takes into account how it's distributed. Okay? Well, how do you do that? Well, we're going to have a look and see how they do it. This can be used as the objective function of the optimization model as opposed to simply maximizing benefits or minimizing cost. All right. So this is the generic problem. We're maximizing social welfare. We're U is the vector of utilities we distribute, and it's a function of the distribution of resources to the individuals or stakeholders, and that distribution is constrained in various ways. And one basic constraint is a budget constraint. So I'm going to give you a number of structural results that only use this budget constraint because it tends to make things more transparent. And again, we're assuming that different individuals have different efficiencies, conversion efficiencies here. Okay. Here are some references if you want to see the details. These slides will be on my website before the end of the day. All right, so I'm going to cover these. We've heard about Rawlsian, Maximin, Leximax, alpha fairness and proportional fairness, special case, Kalai-Smorodinsky, and some threshold models that you perhaps have not seen before. Okay, here we go. I'm also going to look at the issue of hierarchical distribution, because very often, you know, governments and other agencies distribute resources perhaps to the states, and the states may distribute those resources to the cities and so forth, right? It tends to be hierarchical in practice. Well, there's a paradox that arises in this situation that we want to deal with. And it goes like this. Suppose we decide how to measure fairness. We have a social welfare function that measures fairness, and the national government is using that function, and the states are using the same function, okay? So at the national level, we solve the problem as to how to distribute the resources to, you know, individual cities, okay? But we do it through the states, so we give these block grants to the states. Now the states are going to use that same social welfare function to distribute resources to the individual cities. They will get a different result. Even though it's the same amount of money, they're using the same criterion. Just because we have a hierarchical pattern, they will get a different result for the individual cities. So the planners in Washington don't know what's going to happen to the individual cities, even though they model it using the same model that the states do. In some cases, depending on which social welfare function you use. Some functions don't have this issue, others do. So I'm going to call that regional decomposability. If you don't have that problem, the problem is regionally decomposable using the social welfare function at issue. Otherwise, it's not. So I'm looking at this property too. And there's some mathematics here, okay? I won't go into details, but there's a technical property of the social welfare function that is sufficient for regional decomposability. It's something like separability, a little bit weaker than that, okay? There's a theorem there. Now, I'm also going to measure the incentive of people to improve, right? If you have a system of allocating funds, people can game the system. Okay, is there an incentive to improve the efficiency with which you use the funds that you're allocated? Do you have incentive to improve? And if you improve, what's the effect on other users when the problem is resolved to take into account your efficiency improvement? Okay, so we're looking at that too. Okay, what is your incentive to improve, or is there one? Okay, do you do better? Perhaps, in some systems, if you work harder, you get less. And that surplus goes to someone else who's not working so hard. Maybe you don't want that to happen. So we're going to look at that. That's the efficiency, the incentive rate, okay? Also the cross-subsidy rate. If I improve, am I going to take resources from others? If I get better than them, am I going to take some of their resources? Or is my improvement going to benefit other people? We'll call that a positive cross-subsidy rate. Cooperation versus competition. And different functions have different properties in this respect. Okay, so we'll look at those things. The simplest, as I mentioned, is just maximizing utility. That's the one we don't want to use, to be fair, okay? It is regionally decomposable because it's separable, yeah, and you just get what you earn the fruits of your own efficiency improvements, and it affects no one else in this very simple situation. Now, we heard about the Maximin of John Rawls earlier today.
Sorry, quick technical question. So utilities now are always dimensionless or have the same unit?
Utilities are always in the same unit, yeah. Okay. They're not dimensionless, but they're anything you want it to be. It could be health outcomes, it could be access to transportation, travel time, negative cost.
But in the beginning you made an argument that things had different units and you cannot just add them, right?
Yeah, so
but now you assume that they have the same unit.
Okay, no, what I was saying there is that the measurement of inequity is an index that has a different unit than the measure of utility. In fact, the inequity measure is usually dimensionless, like Gini, whatever, or McLoon index, something like that.
So, but how do you make utilities always have the same unit? If, for example, the amount of free time that I have, and I compare it to my costs that I have to pay in dollars, how do you make them have the same unit?
Yeah, well, I don't think I can answer that. That's a problem of application.
So you assume that job has been done by somebody?
Yeah, that has to be done.
Okay, got it.
Absolutely.
If I may say, there are techniques in the area of multi-attribute value functions that basically takes care of that. There's a literature on that.
There must be some modeling challenge there.
Well, certainly there is, absolutely. Yes.
Yes, okay, somebody else has done it.
Yes.
That had been handled by Cox years ago.
There is a technique to do that.
Okay. All right, well, there's actually problems with this one too. So if we have this budget constraint that I mentioned earlier, and we're maximizing the worst off, right? That's the Rawlsian objective. Okay, here's the solution. Everyone's equal. The two parties are equal. Well, what happens here is that this guy is sacrificing a great deal, much more than this guy is sacrificing. This guy could have much more, given the budget constraint, whereas this guy is getting almost his maximum under the budget constraint. This can happen. So, for example, if we have like two patients in a hospital, this guy, is really sick, okay? He's very expensive to treat. This guy is easy to treat, okay? We're reducing this patient to the same level of suffering as the cancer victim, so as to maximize the worst off. Yeah, question in the back, yeah.
Well, this is not what Rawls intended, okay?
Pardon me?
This is not the way Rawls presented this.
That's my next slide. Yeah.
You're just using a principle that was not meant for trade-offs. Yeah.
John Rawls intended this Maximin principle to apply to the design of social institutions and to apply only to primary goods.
Only to wealth and income and wealth, not to all primary goods.
Absolutely, and of course transportation is not a primary good for Rawls. Yeah, absolutely, yes. So I think you can take Rawls out of context, and this is what happens when you do.
Exactly.
Yeah. A comment over here?
No, I was just
okay. All right.
Excuse me, can I ask a question? I saw the difference principle doesn't mean that everyone gets exactly the same. right? It just does it just implies that the most disadvantaged of the society actually guaranteed gets maximized, right?
Well, it's maximized. Yeah, since they're the worst off, it is maximized.
Right.
Yes, that's right.
So it doesn't imply equal for everybody.
In this particular case, for this particular objective function, it does. I mean, for this particular constraint set, you get equality because it's a linear constraint. So when you maximize the worst off, then everyone's the same. In a more complex constraint set, they won't all be the same. Yeah.
In general, you care just about the worst. You don't care about the others, essentially.
That's correct. You just care about the worst. That's right. Okay. Another problem is that if you say you put bounds on the utility you're going to allocate to everyone, then this solution is the same as that one. It has the same maximum of the worst off. They both maximize the worst off, but this solution is wasting most of the available utility. There's another issue with this Maximin objective. Okay. One remedy for this particular problem is to use Leximax, which I'll mention in a moment. Okay? So Maximin has these properties. Okay? It's a sharing objective. It encourages cooperation, but there's still an incentive to improve your efficiency under this one. Leximax says rather than maximize the worst off, first you maximize the worst off, then you maximize the second worst off, then you maximize the third worst off, and so forth. So that's lexicographic maximization. It's a bit more sophisticated than the Rawlsian Maximin. This is regionally decomposable as well, okay? But you still have that extreme solution. In the example I showed you, this is the same with Leximax. Okay, you get the same solution. All right. Now, I mentioned I'm going to go into social choice theory, which is one effort to try to put a mathematical or even philosophical foundation on some of these social welfare functions. One issue that arises is that we have to assume a certain degree of interpersonal comparability of utilities. To what extent does it make sense to compare utilities across people? Okay, does it make sense to say, I have twice as much utility as you do? Okay, so we have to make a decision on that comparability issue. But if you do, then you get some results. So people use axioms like this. They're pretty straightforward, pretty non-controversial axioms for the most part. But the big one is the degree of interpersonal comparability. Okay? I think it's not widely realized how strong these assumptions are, even though the results are quite impressive. There's something called unit comparability, which means you can compare utility differences across individuals, but not absolute levels. Okay? If you make that assumption, then your social welfare measure must be utilitarian. It must be. Oh, that sounds really impressive, huh? The problem is that's a very strict limitation on the degree of interpersonal comparability. For example, you can't ask who's worst off. You can't ask that because only differences are comparable, not absolute levels. Okay, so it already rules out Rawls by definition. Okay. Another one is level comparability, okay, which makes it possible to compare levels across individuals, so you can tell who's the worst off, but you can't put a numerical value that's meaningful on it, basically. Given this, then you have to use a Maximin or a mini-max, one or the other, okay? But again, that's a very strong limitation on the degree of interpersonal comparability, and it rules out all the other social welfare functions I'm going to show you in this talk. Okay, so these results are interesting historically, but a lot of assumptions behind them. Okay, all right, now, one very interesting social welfare function that's been used by engineers for some time is alpha fairness. It looks like this. The social welfare function is given by this thing, okay? It's basically the integral of a power law, something like that, okay? And it has a closed form solution that you maximize subject to a budget constraint. Okay, so it has nice properties. Alpha indicates the degree of fairness you want to impose. When alpha is 0, you become utilitarian. And alpha goes to infinity, you become Maximin, become Rawlsian. Okay. a special case is alpha equal 1. That's proportional fairness. Okay. One interesting consequence of this is that there are cases where an egalitarian distribution can be equally desirable to one in which there's an arbitrarily large inequality under alpha fairness. Think about that. This has an axiomatic derivation I'll show you in a moment. Okay, so here we have 8 individuals. We're splitting up. Individual 1 is very efficient. His cost is very low. This guy is very difficult to satisfy, to generate utility for. And this is the alpha here. Okay, so we're becoming more fair as you go up the scale. So as you see, as you go up the scale, people become more equal. As you go down the scale, the efficient guys win out. This black line is the total utility you generate. So there is a cost to equality. Okay, more equality, you have less total utility. All right. This has nice properties, regionally decomposable. Okay, everyone has an incentive to improve. Okay, and that incentive increases with your conversion efficiency. Okay. There is a cross subsidy to others when alpha is greater than 1. So if alpha is greater than 1, you're more fair. Then if I improve, others are going to benefit from my improvements. If alpha is less than 1, it's a dog-eat-dog society, right? When I improve, I'm going to take resources from others in the optimal solution. Okay, so 1 seems to be the critical juncture here, doesn't it? Yeah. This, as I mentioned earlier, is the Nash bargaining solution. This is actually the beginning of social choice theory. Nash published a paper in 1950. It was the first paper in this field. He was actually one of our students at Carnegie Mellon. And my colleague, Jerry Thompson, got him into the Princeton PhD program where he worked with Albert Tucker, the game theorist, and who gave us the prisoner's dilemma. Okay, so we have something of a connection with Nash. In fact, Tucker was my advisor at Princeton too. So that was the first paper I read in mathematics way back 100 years ago. Okay. All right. So when alpha equals 1, we allocate utility in proportion to your conversion efficiency. That's why it's called proportional fairness. So the more efficient you are, the more you get, but you don't get everything for being efficient. It's still spread around to some extent. Okay. This is fairly widely used in engineering. There's no cross subsidies for this one. Everyone is on. Okay. And it has a very nice solution. Basically, this is the starting point where you start with your utilities. And to find the Nash solution for the utility allocation under this feasible set, you maximize the area of that rectangle. Isn't that cool? Okay, a very nice geometric interpretation. Now, Nash had an axiomatic derivation for his criterion. Okay? But it assumes a type of interpersonal comparability known as scale invariance, which basically says if I compute my utility in dollars and you compute your utility in RMB or yen, it doesn't matter. We don't have to convert one to the other. We get the same result. Okay? Everyone can use his own currency without converting to the others. That's a bit of a strong assumption, right? Perhaps it's suitable for negotiation. In fact, this was the context in which Nash proposed this criterion, a negotiation setting, rational negotiation. But it may not be suitable for gauging fairness in other cases. It's a strong assumption. Okay. There's also bargaining justifications, other than Nash's, that come along. Harsanyi also won Nobel Prize, as well as Nash, and he gave a derivation that shows if you bargain in a certain rational way, due to Zeuthen, okay, you will arrive at the Nash bargaining solution. And there's some more results based on equilibrium modeling that give a similar result. Okay. Okay, so there's some justification for this. Okay. On the other hand, does fair and rational negotiation lead to justice? This is a very deep issue in philosophy. Okay. Does procedural fairness yield substantive fairness? Depends on your politics, right? Yeah. If you're Margaret Thatcher, you would say yes. Okay. Now, there's an axiomatic derivation for general alpha fairness, and the key assumption here is this thing, axiom of partition. So good luck understanding that. So what does it say? It says if you partition your population into two groups, okay, then the ratio of the social welfares of the two groups is equal to some mean of the ratios within each group. If you have two distributions, U1 and U2. Okay. So you can sort of split things up and you don't change the ratio of social welfare with respect to two distributions, except you have to apply some kind of mean. It turns out this has to be a power mean or a geometric mean. Okay, so the mathematics is quite complicated, but you can derive alpha fairness as well as some entropy-based measures using this set of axioms. It's a powerful result. It's just that it's very difficult to interpret this axiom in practice. And personally, I don't know how to interpret it, whether it's appropriate for a given application. But you can think about it, something to look at. It deserves more research, I think. In fact, I had Land at a conference. I invited him just last week to present some of this work, and I asked him, how to interpret this? He didn't know how to interpret it. Okay. All right. That's a problem there. So here's an example of alpha fairness. I think it's pretty cool. So this person is a colleague of mine in engineering, Destiny Knock. So here we're adding to the electric grid in Liberia. So at the moment, when this study was done, only Monrovia had a decent electric grid. And basically no one else had electric power. So if you use alpha equal 0.1, essentially a utilitarian solution, you can see that two cities get all the goods, essentially. It's the most efficient because this is where most of the people are. So you maximize utility by taking care of those guys in the cities. As you increase alpha, you see it tends to spread out. So finally we get up to alpha equal 1. This is Nash bargaining solution. It's pretty much spread out. Not quite equal, but much more egalitarian. Okay, so now you're thinking, okay, which of these alphas are you going to choose? That's a problem with alpha fairness. Okay, which alpha do you want? Well, one thing you can do in a case like this is to sort of establish an industry standard. You sort of arrive at a consensus for an alpha that seems to make sense and satisfies people, okay? And then you can apply that same alpha to the next case and make a reasonable, a meaningful comparison with what you've done before. Is it more fair or less fair than we usually do in this field? You can do something like that, and this is what they did. So they actually surveyed engineering students, graduate students in engineering, and showed them a set of maps like this and says, which ones do you like? Which ones are a reasonable balance between efficiency and fairness, okay? Yeah.
Could you explain that in Alpha 1, Monrovia have 59 units.
Yeah.
And the town, basically, the next one, 67. It's I was expecting all of them to be kind of equal.
Yeah, well, it's because Monrovia already has a good deal of electric power provided. They already have a power grid. So we're adding capacity to this system.
This is the added capacity. Okay, I understand. Okay, that's right. That makes sense.
So you see, the cost of fairness here is quite substantial in the total amount of electricity generated to the nation. Fairly substantial. So what is a reasonable alpha to use here? Well, they, as I said, used graduate engineering students, used their intuition, to sort of, in this survey, and this is the results of the survey. This is the frequency of the number of people who preferred solutions with this alpha in the background, based on this degree of alpha. See, most people wanted to be quite fair, rather idealistic group of students. Okay. The average was 0.81, so they went with 0.81, and that is this solution right here. Coincidentally, that's sort of interesting because that's where the plateau drops off in this efficiency graph as well. Okay. Now, if they had done the same survey in Liberia, they would have been even more fair because sub-Saharan Africa has a very strong egalitarian ethic. I learned that when I was living in Zimbabwe. So they have a very strong emphasis on fairness there, more so than we do. So that's one way to approach this issue. Okay. Now, there is a problem, another problem with the Nash bargaining solution, and that is if you increase the amount of resources available, sometimes people end up being worse off. We had a discussion of that earlier. Okay? So here we have an original feasible set. This area here is the original feasible set. We have 2 persons. Okay? Now we're going to enlarge the feasible set. The Nash solution in each case is given by these 2 dots. So as you see, when we enlarge the feasible set, person 2 gets less. It's cut back, even though there's more resources. So Kalai-Smorodinsky thought this was irrational, so they proposed another solution to this problem. And their solution was this. You look at the ideal amount, the maximum amount of utility either party could obtain. You draw a line to the origin and take the intersection with the feasible set, intersection with its boundary. And as you see, both parties improve when you improve the degree of resources available. Okay, so you can also give bargaining solutions and axiomatic arguments for Kalai-Smorodinsky. You just change the axiom slightly. You change the axiom to insist that you have this monotonicity property, and you get, instead of Nash, you get Kalai-Smorodinsky. This thing is sometimes regionally decomposable. It's interesting. Okay, it depends on the parameters of the model. If the model has solutions in which sometimes you will take resources from the states rather than give them resources, if that's an allowed solution, then it's not regionally decomposable. Otherwise, it is. All right. Now, this is a set of methods. By the way, I think I'm moving faster, so we'll have time for questions. I know I'm keeping you from lunch, but we have time for some discussion as we go through here. Okay, so yeah, these threshold methods came from these guys, Williams and Cookson, British, and it's an interesting set of ideas. Okay, there are 2 kinds of threshold methods. They combine utility with the Maximin, okay, in a different way, not just a convex combination. They combine them. And one is a utility threshold, which basically says you're concerned about fairness, ordinarily, but if fairness becomes too expensive, then you're going to start to switch some of the people to utilitarian, something like that. Okay? An equity threshold is the opposite. You're concerned about equity primarily, but when, did I say that backward? Oh gosh, I think I said it back. The utility threshold means you're concerned about equity first. I got it backwards. You're concerned about equity first. Then when the utility cost becomes too great, you switch. And for this one, you're concerned about utilitarian first, okay? And then when it becomes too unfair to some people, you start switching to equity. It goes like that. So the first one is really, is cases where equity is very important, you know, sort of like medical situation, triage. You want to be fair to everyone. People are very sensitive to the fairness issue or task assignments. With equity, this is in telecom. You want to have an efficient system, disaster relief. You want to relieve as many people as possible, get them out of those earthquake-prone buildings, whatever, as quick as possible. Okay, yeah, and traffic control. So these 2 criteria have different set of applications, I think. So this is utility threshold. So in the middle here, we have a Maximin set of contours, and then we have utilitarian contours out here on the edges. And we have this parameter delta, which marks the boundary between the 2. Okay, so in this case, we have a feasible set under this curve. Okay. This is the Maximin solution. Okay, the 2 are equal. Okay. Well, this solution has a problem, right? Because look what happens. In order to improve person 1's utility a little bit, we have caused person 2 to lose an enormous amount of utility, right? Person 2 is sacrificing a great deal of utility just for a small improvement in person 1's utility due to the slope of this curve. You say, well, this is just too expensive. This is unfair to person two, right? He's sacrificing too much for the other guy. Well, we try to deal with that by looking at the solution for this combined set of contours, and the solution there is actually up here. So person two doesn't lose so much, but still person one is not too far below what he could be if he got all the resources. Okay, so it's another way of compromising, and in fact, this can be generalized to n-persons. Not obvious how to do it, but you can do that. And the delta has an interpretation. The interpretation is you care more about people who are within delta of the worst off. If a person is within delta of the worst off, then he gets more priority, he gets more weight in the utilitarian calculation, and that weight is equal to the number of people who are worse within delta of the worst off. All right, so the delta has sort of a practical meaning. You know, how badly off do you have to be relative to the worst off to get special treatment? You decide, and that's the delta. Okay, it's a little better than the alpha, maybe. Okay. Now, when you solve this problem subject to that budget constraint, you get a disappointing result. The solution is either purely utilitarian or purely Maximin. So here's an example, right? So here we have a Maximin for this particular slope of the budget constraint. You change the slope, you get a purely utilitarian solution. Okay, so it doesn't really help a lot. On the other hand, if you have bounds on the utilities, it gets much more interesting. You limit the amount of utility each person can enjoy, which is really what happens in practical situations. For physical reasons, if nothing else, you can only improve someone's utility so much with resources. With those bounds, it turns out that exactly one person at most will be between his upper bound and the smallest utility granted. So there's a very highly structured solution to this problem. Okay. This thing is not regionally decomposable. Okay, so the states can get different solutions in the federal government using the same social welfare function. Is that good or bad? What it means is that, you know, if the state of Alabama is solving this problem with the money they got from Washington, they're going to get a different solution unless they take into account the rest of the country when they're solving their own problem. If they take into account the whole country, to be fair, like the guys at the feds do, they'll get the same solution as the feds. But if they take into account just what they are doing, they won't get the same solution as the feds. Is this good or bad? Well, it's both, right? You might say, you know, it shows it's a more subtle and more sophisticated because every state has to be sensitive to everyone else, the whole country. On the other hand, it's harder for the feds to manage this situation because the states are going to go their own way, even if they use the same criterion.
So when you have hierarchical structure, will the budget depend? Will the upper bound depends on the higher level or lower level? Who decides that?
Yeah. So this is the case where we have upper bounds. Okay, it's usually decided just by the physical situation, right? So if you have a patient in the hospital, just lavishing all the resources, all the treatments is only going to improve the patient so much. So that's an effective upper bound. So it's usually something like that.
So it's not decision of the upper level.
Yeah. Okay. So that's utility threshold. Now the equity threshold is the opposite. Okay. So here we have utilitarian contours in the middle, and then the Maximin contours on the edges. Okay. Yeah, and it looks like this. Okay. And this can be generalized as well to n-persons. This actually becomes a linear programming problem. It has that nice feature. It's easier to deal with. Okay. The other was mixed integer programming. Okay. And what does the delta mean? It's the opposite now. So before, a small delta means that you're more utilitarian. Delta 0 is strictly utilitarian, and delta becomes huge, it becomes Maximin. Here it's the opposite. Okay. Small delta means that you're more fair, and big delta means you're more utilitarian, just the opposite as before. And what does it mean? That means that if you're more than delta greater than the worst off, then there's no social value in giving you still more, unless you give the worst off guy just as much. Okay? So if you have the rich guys who are more than delta better than the worst off, okay, There's no social value in giving the rich guys even more money unless you improve the poorest by the same amount. And the delta decides whether you're a rich guy or not. So you decide which one you like, okay, which delta you like in a case like this. See what people can agree on. Okay. The solution to this one is interesting. Okay, it's much more interesting than the other one was. And here's a little example. These are the 8 guys I showed you before. Remember before, they were getting more equal as delta gets, as alpha got large. Here's more equal as delta gets small. So there's more, it becomes Maximin here. They're all the same. Okay? And for more utilitarian, you see how they kind of rise and drop off in an interesting way on this criterion. Now, you can look at this and think if it's reasonable for you. Okay? This is the total amount of utility, so there is a cost of equity, the thick green line. Okay. This is not regionally decomposable, as you would expect. The cross subsidies are quite intricate. I won't go into details, but they're quite interesting. Okay, it's not obvious at all. All right.
So I have a big picture question on this. So the design of objective function is something that is, in some sense, a modeling task, right? One has to get together and say, what do we want to do? And you outline here a lot of examples. And then you say, of course, well, which one you pick, that's something you have to get together in a room and talk about it.
Yes.
In a sense. But I'm wondering, is there some one hierarchy level higher, right? Like a meta principle or something, that if I optimize that meta principle, I would get as an answer, this is this respective objective function that comes out of it. For example, overall happiness of people, or something like this, right? That is really, really difficult to quantify.
Yeah.
But is there something like this behind?
So I'll give you my opinion. Okay, so you mentioned more happiness for more people. That's the Benthamite, utilitarian objective. So that's usually interpreted as simply maximizing total utility. That's the classical interpretation of that.
Yeah, but there's many counterexamples where this happens.
Yeah, but you don't want
because
that.
we're rational, right? People are rational.
I think if you look at the foundational arguments for utilitarianism, you look at them more closely and reason more precisely, you can begin to justify some of these equity-sensitive objectives. I think with a more sophisticated derivation of a Benthamite type of reasoning. That's my view. That's what in fact, I'm working on that. Yeah.
But, I mean, you showed several ones, and you gave a nice characterization that it's not one is intrinsically better than the other, right? So if a politician now asks you, which one should I choose?
Well, it's a matter of, that's a cultural issue, right? It's a matter of what people are willing to accept.
Yeah.
And essentially what the sort of results you're getting from a particular criterion are acceptable to people in the long run.
Right, but that's very important because happiness of people in some sense translates into votes.
Yeah.
Right?
Yeah, sure.
So therefore there should be some higher principle that sort of leads to different outcomes.
Yeah, well, of course, even in democracies, right, we have human rights as well as majority rule.
Right.
Yeah, so you can't simply think about votes to have a viable democracy. It's the same here. You can't.
So your view is there is no higher principle that would lead to which to choose?
I think there is, but I can't give it to you today.
Okay.
Yeah. Yeah. Yeah.
All right, great.
I don't think it's in the literature, no.
Okay, great. Yep.
No. Some people, of course, many people have claimed, Parfit, for example, the philosopher, thinks he has a general, derivation. I'm not sure. Yeah. Okay. Derek Parfit, who's a guy at Oxford. Okay. Okay. All right. So someone mentioned the problem with Maximin. It only cares about the worst off. Okay. That's a weakness. And there are a lot of cases I'm going to show you on in a minute where that weakness really is a fatal weakness. So we want to go to Lexa-Max instead of Maximin. So we take into account everyone's level, not just the very worst off, and combine Lexa-Max with some kind of utilitarian using a threshold idea. So that can be done. In fact, I worked on that with a student. And you get, actually, you get a series of optimization problems and mixed integer programming problems that look something like this, okay, with the objective function. And the solution is something like this. It's pretty interesting. Yeah, and I'm going to show you an example of this. Oh, this, by the way, is the solution you get using this Maximin combined with Lexa-Max, as here the delta is becoming more fair as it increases, and you get people becoming more and more interesting in kind of step function, step patterns, an interesting pattern. Okay. And all this stuff is computable in advance, all these intervals. Okay, so this is a solution you get simple, subject to a simple budget constraint. Okay. Okay, this is not regionally decomposable. The cross subsidies are interesting, okay, non-obvious. Okay. As you're more fair, generally speaking, as you become more fair, you have more cooperation in the incentives. You're incentivized to cooperate more. That's the basic story here. Okay. Now here's my example. This is from Istanbul. Okay. I lived in Turkey for a while, and I know about the earthquakes there. Okay, one occurred while I was there. It's horrible. Okay. Yeah, and I wasn't near the earthquake. I was in Ankara. The earthquake was over near the Sea of Marmara, so it didn't affect me. Yeah, so the problem here is to locate earthquake shelters in Istanbul. Okay? So that when the water goes out and the power goes out, you can go to a shelter, and you want a shelter that's easy to get to. It's close because the streets are going to be torn up and so forth. So in this model, from these guys, she is one of my former students, I'm very proud of. Okay. There are 50 neighborhoods and 50 potential shelter locations. Okay. This is the solution. Let me explain this plot. Okay. There's several interesting features here. Okay, so on the bottom here we have this delta. This is how far above you have to be above the worst off so as not to receive special consideration. Okay, if you're within delta of the worst off, then you get special consideration for fairness. Okay, so that's the delta. So you're becoming more fair as you go up here. This is the distance from the nearest shelter. Okay, these are negative utilities. Okay, so distance is negative. All right. Okay. Each of these lines here corresponds to a neighborhood, one of the 50 neighborhoods. Okay, so as you see, there's a sort of a pattern, at least down here. As you increase the level of fairness, then the guys who are far from the nearest facility, the nearest shelter, tend to get closer. They tend to get closer. This green region means you're within delta of the worst off if you're in that region. Okay, so you're getting special consideration. So as we increase the delta, these guys are coming closer and closer to special consideration, and then they get in here and then they're much better off than they were before for a smaller delta. So you'd expect that. Now there's some strange things going on. Like these guys are very badly off, but when the delta increases, they get a little closer, then they don't get any closer at all. These are the very worst off in the whole city. So why not? It's because there's no potential shelter location close to them. They can't get closer. So if we only consider the very worst off, we're only thinking about these guys, okay? And the problem becomes trivial because they can't get any closer than this. And we don't care about anyone else. So you just simply can't use that Maximin criterion in the mix. You have to use a Leximax. If you use Leximax, you get this, okay? You see what happens up here. These guys are lucky, and to become more fair, they become a little bit less lucky, okay, because they're yielding some privileges to the guys who are out on the outskirts of the city, okay, to make room for them. All right. There are some subtleties that goes up and down. These can be explained, actually. I won't go into it now. But I think this is what you want. You want a nuanced solution that takes into account all the complexities of the situation. Yeah?
Is there kind of like a general theory for like practical significance of, declining utility, or is that more of just like a modeling question? Like obviously if you decrease a little bit from already being very close to a shelter, it's maybe practically not that significant, but having like a large jump from far away would be practically significant. Is there maybe like a theory there, or is it kind of more modeling?
I think I should defer to the rest of the audience on that one. I don't know of a theory, but maybe someone can help us on that.
Well, in economics, it's a characteristic of the decision makers. It basically is it's an attribute of the decision maker, of the people involved.
Yeah, revealed preferences is one approach. Personally, I have problems with revealed preferences, but that's a commonly used approach. Yeah. Okay. So this sums it up, okay? this is the solution structure for each of these various models, and the properties that I mentioned, the decomposability and the incentives and sharing. Okay, so I think we're going to get to lunch in a timely way. Any other?